or physics, the length of this arc is the radius times the angle, as long as your angle's in radians. Where does that formula come from? Right there. Guys, we just did it, right? We just generated that formula. All right, that's awesome. See, I got to stop doing that stuff because that's not part of the plan today. All right. All right, now if we go to three-dimensional space, it's the same formula. Nothing changes. So you don't need to read through that. It's the same condition. You can't cross over itself. You recognize this function. What does that draw? Right? We called it a spiral last time. It's not. It's more like a spring. Spiral, you think of it like growing, getting bigger as you go out. This is like a spring. It's the outside of a can, going up the outside of a can, or like the helix thing. So find the arc length of this three-dimensional vector curve from the point 1, 0, 0 to negative 1, 0, pi. So there's a couple of things I need if I'm going to use this formula. I need to know limits of integration, right? A and B. Am I given A and B? Explicitly, is it right there in front of you? No. Can you tell me what A and B are? A is what I plug in to get this point. B is what I plug in to get this point. So what would I have to plug into this vector function to get this point? It's another one of those obvious ones. It's given away by the third component. T is 0, right? If T is 0, check it in here. Cosine of 0, 1. Sine of 0, 0, 0. So you get 0, right? So T is 0 down here. That's what would start us off at that point. What would end us here? T is pi, right? So check it again. You could plug pi into these. You should get these three. So we stop at pi. And now I need the magnitude of the derivative, don't I? Magnitude of derivative? Let's do that right here. What is the derivative of this vector function? Negative sine t. It's kind of a, that's funny. I said this on, I was making the solutions, the homework problems for 10.8. I finished them today. And when I was doing it, I was sounding like a broken record because almost every single time I was doing a problem, it always had sine and cosine in it. And that's the way that the author saves you, when you do that square root, it turns into something nice. If it didn't, can you imagine integrating something that would be really like crazy? Right? Then you'd have to pull out your old Cal 2 stuff. What is this last one? 1? Now the length. Square root sine squared t plus cosine squared t plus 1. Which is what? Square root of 2. So we're just integrating root 2 with respect to t. And if you do that, you should get pi times root 2. I'm not going to do it. That's how long that curve is. I might have the picture of it also. Let's see. Yeah, there's the picture. So you'll notice, well, I've got a bunch of stuff in the way here. I have the computer telling me what t is and what the arc length is. So I'm measuring that red piece until I get to, where were we going? Pi? We're only going to pi, so pi is like 3.14 something. I just put it in here. Pi. Okay, so someone on their calculator, what's pi times root 2? Just verify for me. What's pi times root 2? 4.4? Really? Oh, it didn't do. Oh, it didn't take the pi. Okay. Why didn't it take pi? That's weird. Oh, I didn't enable dynamics. That's why. There we go. There we go. 3.14, 4.44. As long as you can integrate the magnitude of the derivative, you can find the length of any curve, as long as you have the vector function that draws it. Can I share that problem? Okay. Daniel, right? Daniel? Sent me something that he found online where it was they were measuring the length of a DNA strand, a chromosome. One chromosome. It was we think it was a problem, right? You think it was a problem from a math class? It's hard to say, right?
I just typed in because when you did the double helix,
yeah,
it didn't exactly look like DNA. I was like, I know there's a function out there for the DNA.
Okay.
I just typed the DNA vector helix.
Okay. Yeah, so he was able to find the vector function that models the chromosome, right? And in this problem, they were measuring the length of it. And I guess it was a realistic problem, like those were actual measurements, because what did it turn out to be, like 3 inches?
2 meters.
2 meters or something like that. So if you were able to take that strand and unwrap it and pull it, it would be 2 meters long. So like 2 of these. It was a single chromosome? Really? Huh? Interesting. But it was cool. All right. Why don't you take a minute? Guthrie 210. Let's just do this once. Let's find the arc length. Let's just take the derivative, find its magnitude. We won't do any of the integration. All right? What's the derivative of this guy right here? Three t to the 1/2.
1/2.
Derivative, not anti. Right? -2 sine 2t. That's your derivative of cosine 2t. Then derivative of sine 2t is 2 cosine 2t. All right, there's your derivative. And then the magnitude. Square root 9t, right? Square this, you get 4 sine squared 2t. And then square this one, you get another 4 cosine squared 2t. What can you factor out of these two? A 4. And then that becomes a 1, right? The fact that they both have 2t in them, that doesn't matter. So you have just a 4 out here, right? So what does this turn into? Square root of 9t plus 4. And that's what you would have to integrate. And that would integrate pretty straightforward. You could do a u substitution if you want, just basic, let 9t plus 4 be u, and then integrate up. But see, it's a little more complicated than what we've been getting. We've been getting constants, haven't we? That one's a little more involved, but definitely not crazy. You think you could take it the rest of the way? Yeah? All right, that brings us to the last topic in this section, which is called curvature. It's a way of measuring, okay, the curvature of a vector function is a number which represents how quickly a curve changes direction at a given point. And there are 2 formulas for calculating the curvature. We use this K here for curvature. It's, you recognize this? Capital T was the what? Unit tangent vector. It's the unit tangent vector. Okay, it's the derivative of the unit tangent vector divided by the derivative of the, sorry, magnitude of that, divided by the derivative of the position.
You said how fast it does what now? Curvature?
How fast the curve is curving. How fast it's turning, right? That's one formula. Sometimes this is easy to compute, sometimes it's very difficult to compute. There's the alternative formula. It brings in the second derivative of the position function. So, and you have to do a cross product and a magnitude. Does anyone have the book with them? You do? Just want to look at something on that. Let me make sure it's not a typo. You're good. Curvature. Yeah, okay. All right, that's it, two formulas. Now, I want to show you like a picture of what's going on. I'll do that as soon as, well, there. Look at this one. I'm gonna press play here. Well, there's no play. I don't have a play button. There it is. So I want you to notice if you're moving along this curve, which is a unit circle, right? Then the curvature, we're measuring at any single point its tendency to want to turn, right? Does it make sense that on a circle, at every point you should have the same tendency to turn, the same curvature? Well, if we compute the curvature, look at what it is. It's 1. It's always 1, no matter where I am. So the computer is actually changing t and computing curvature, and every single time it does it, it gets 1. Let's actually verify that ourselves by finding the curvature of this. The answer should be 1. So how do you want to do it? You want to use the first formula or the second one? Second one? The second one requires a cross product, doesn't it? Did you see it had a cross product? And couldn't we only do cross products on vectors in three-dimensional space? Yes? There's a workaround. If you want, let's do the workaround. I like the workaround. This is R of t, right? What I'm going to do is I'm going to extend R of t into three-dimensional space. Watch. Now R of t is in 3D, isn't it? Does that draw the same curve? That's still drawing me a circle in the xy plane. The z coordinate is always 0. So it's like on the xy plane. Same circle. It's just now we've moved off the sheet of paper and we're out there in three-dimensional space. Now we can do it. So do I have to show you the formula or do you all have that down? Okay. All right. I could write it down, but you could also print out the notes that are provided for you or bring a laptop. So what is it? The curvature is the magnitude of the cross product between the first and second derivatives of the position function divided by the magnitude of the first derivative of the position function cubed. That's it. So we need the first and second derivatives, don't we? Let's do the first derivative. First derivative is, what is the first derivative? Negative sine t, cosine t, 0. What's the second derivative? Negative cosine t, negative sine t, 0 again. Do I understand this, my first and second derivatives? What am I supposed to do with these now? Cross product. Now cross product is where we had to cover up the I and do that little thing and cover up the J and do that little thing. That's what I'm about to do. And I wrote them down vertically intentionally so that I could actually do this cross product. But I'm going to put the answer over here. What is R prime T crossed with R double prime T? So we've got cover up these, and then go ahead. Cosine here, and then that's what, 0? And then 0? Yes. This is a vector, isn't it? 0. And then I get 0 again when I do that?
Yep.
Damn, nice. Last one. Sine squared t minus negative cosine squared t, which is really sine squared t plus cosine squared t, which is 1. What is the magnitude of this? So what's the magnitude of this? Well, it's the magnitude of that, which is just 1. Square root of all those squared is just 1. And then I need to divide it by the magnitude. So that's the numerator is 1. The denominator is this cubed. So we have to take the magnitude of this. But what's the magnitude of this? It's 1. So 1 over 1 is 1. So the curvature is 1. That's boring, right? But you get the idea of how you'd use that formula. And not only that, if you have a two-dimensional vector function, how you can extend it into three-dimensional so that you can get the curvature using the second formula. Here's an example of a vector function that does not have constant curvature. Like the circle is obvious, right? If you're on the circle, you've got that same curvature the whole time. This is a spiral, and it's a tighter spiral in the center, and it kind of gets wider as you get bigger. So does it make sense that the curvature should be large in the center and get smaller as you move out? So a larger curvature is like, how fast it's turning. So look in here. I think I can slow it down. Or I'll just pause it. Move it back to the beginning in here. Right there at the very beginning, look at the curvature at here at time 0.01. The curvature is what? Almost 2,000. But as I move out, notice that number's gotten smaller already. Now look at that, not much further away. At 0.12, the curvature is 23. And then as I move out further and further and further, now my curvature, look, at 1.2, the curvature is 0.05. So it's kind of like, if you've ever been on one of those carnival rides, where you put you in there and they start whipping you around, curvature is like how much feeling you have of, getting, what do they call that? Force that wants to pull you in, and isn't there the force that wants to pull you in, force that wants to pull you out? Centrifugal and centripetal. There's two different ones, right? I've heard there's really only one, but okay, we're not going to get into that. All right. Find the curvature. What formula do you like?